You certainly don't need to be an expert in cryptography in order to work with Plutus and Cardano. However, there are two important cryptographic concepts, hashing and digital signatures, that play quite an important role. So I wanted to briefly remind you of those two. So let's start with hashing. Hashing takes as input a byte string, here represented as hexadecimal text, and produces another byte string as output. And in this little demo here, I can type some text into this top text area here, and this text is then encoded to byte string, and that byte string is hashed. And there are actually a couple of things I want to draw your attention to. So first of all, the output byte string always has the same length. So in this case, we are using the SHA-256 hashing algorithm, and the output will always be 32 bytes long. So no matter how long my input text is, this output is always fixed. It always has a fixed length of 32 bytes. And this works for texts of arbitrary length. So for example, I can just make this longer here, and we see that the output will always have this fixed length of 32 bytes. The second interesting thing about hashing is how unpredictable it is. So if I make a very small change in the input, for example, remove this exclamation point, if you look at the output at the hash, it's completely different. So it's not the case that a small change in the input results in a small change in the output. On the contrary, a small change in the input has a completely different result. In particular, that makes it very difficult to come up with an input text that produces a hash with some property. For example, for proof of work blockchains, miners try to solve these little hashing puzzles where they try to produce inputs that have a certain number of zeros in the resulting hash. And actually, it's not easy to do that. So let's say I just want 1 0 in the beginning. I can try some arbitrary text. I just keep going until the hash starts with the 0. There was one. So it took me quite a while to come up with a hash that starts with a 0. I mean, on average, of course, every 16th input text should start with 1 0, and every 16 times 16, so 256th input text should start with 2 zeros and so on. And the point is that hashing algorithms are designed in a way that makes it impossible or practically impossible to find such inputs that hash to an output with certain properties, like having a couple of number of zeros in the beginning, without just brute forcing it and trying lots of input texts. In particular, given a specific hash, it's practically impossible to come up with an input that has that given hash as its hash. Of course, if you think about it, there is an infinite number of possible input texts, because input text can be arbitrarily long. But there's only a finite number, albeit a very big finite number of possible hashes, because the length of the hash is fixed to 32 bytes. So there are only 2 to the power of 256 possible hash values. And seeing as there are infinitely many input values, there must be infinitely many input texts that have the same hash. However, in practice, it's basically impossible to find two texts that hash to the same value. If you manage to do that, that would be a so-called hash collision, and it's practically impossible to find one, at least for SHA-256. There have been other hashing algorithms in use in the past where such collisions eventually have been found. But as far as I know, nobody has ever managed to find one for SHA-256. And that is a property that the security of Cardano or other blockchains critically relies on. So it's always assumed that it's virtually impossible to find an input text to a given hash. So that's what I wanted to say about hashing. Now let's look at digital signatures briefly. So the point of digital signatures, as the name suggests, is to digitally sign documents. Actually, again, byte strings. But to make the demo prettier, I again allow arbitrary text as input, and then under the hood, I first encode it as a byte string. So let's take some message. Let's say I want to digitally sign it. So for that, I need a key pair consisting of a private key that only I know and a public key that is publicly known. So I can generate such a key. And once I have a private key, you can derive the public key from that, but not the other way around. And once you have the private key, you can sign the given message, and this is the resulting signature. As there are many different hashing algorithms, there are also many different digital signing algorithms, but the principle for all of them is the same. Now let's say on this side, there is some recipient that wants to check whether I really signed this message. So I give him the message and I give him my public key and I give him my signature, and then he can verify that indeed this signature belongs to this public key and this message. Now I want to point out several things. First of all, the same signature is only good for this message. So if there is another message, for example, with a question mark, but I use the same signature, then verification will fail. So the signature is tied to the message. Secondly, it's also tied, of course, to the key. So if I use a different key and try to verify, it's also invalid. So the important point is that the signature will only verify for the specific message and the specific public key. And that guarantees that the message hasn't been manipulated and that the signer of the message is indeed the owner of the private key that belongs to the public key. So both hashing and digital signatures are used at a lot of places in virtually any blockchain, in particular in Cardano. It's digital signatures that keep your money safe. So for a transaction to spend your money, you have to digitally sign the transaction. And the features, the cryptographic features of digital signatures ensure that that is secure and that only you, only the owner of your private key is able to spend your money.